Okay, so this class and next class we'll be talking about the Galton-Watson process. Okay, so okay, which I mean it can be seen as a model for different things. I guess being that we are in the world that we are living in, this will be a model for the spread of coronavirus. So the idea is going to be that each person infected has each person infected infects k persons with probability pk. Okay, and the idea is that this probability pk, so p of k, the sum of pk with k equals to 0 up to infinity is going to be equal to 1. Okay, so this is a distribution. This p of k is a distribution which is defined by the values of the probability of infecting k people at any given time. Okay, so we're going to assume. So each person infected infects k persons with probability pk after 2 weeks. Okay, and this is the gestation period. Okay, so we're going to assume that initially there is one person infected. Okay, and this is what we're going to call Z0. Okay, so Z0 is equal to 1, and then Z1 is equal to the number of people infected after 2 weeks. Okay? Now, the point is that each person infected, so now we need to go back to our assumption. So each person infected infects k persons with probability pk. So this is the number of people. So this zeta 1 will be a random variable. Okay, and here we are going to assume that the original infected person has died or has gotten cured. Okay, and so then, so the zeta 1 is the number of people infected after 2 weeks by patient 0. Okay, then Z2 is also a random variable. And it's going to be equal to the number of people infected after 4 weeks. Okay, and then here we are going to assume that the people infected in the first 2 weeks, in the first 2 weeks, have either died or gotten cured. Okay, so this thing here is called a branching process. Okay, so we start with one person, patient 0. And then we have the distribution pk. So this guy has, let's say, offspring, which is like considers of like sons and daughters. Okay, this is C0. The sum of all of these guys is C1. Then C2 is a branching process again. So this guy can branch into 2 guys. This guy could have died and initially and not given it to anybody, and this guy could have branched into 3 people. And then we will have, and the point is, this person has branched into this many people, and the people in the stage above are not counted anymore because they have either died or gotten cured. Okay, you can actually make this model a bit more complicated, but the idea is that even this simple model is interesting mathematically, and so the point is to start with something simple and then become a bit more complicated. And so the point is that then you need to keep going. C3, this person have died, this have branched into 2, branch into 2, and then you get C3, C0 is equal to 1, C1 is equal to 3, C2 is equal to 5, and then C3 is going to equal to 8, okay, and so on. Okay, and then we're going to ask a couple of questions is, when do we know if the virus will go extinct? Okay, so this is one of the questions that is happening now in Brazil. I mean, there is a growing and growing population, but could it be that eventually, randomly, this virus disappears? And what is the probability that the virus will disappear? And what are the things that control the probability that the virus will go extinct? Okay, what controls the probability that the virus will go extinct? So, okay, and this is something we're gonna look further on, but the idea, at least the first answer that you should be, you need to look at the expected value of the random variable of how many persons, each person infects k persons with probability pk, okay? So let's call C the random variable, or let's call, I guess, X the random variable that X the random variable of infected people by a single person. Okay, so X is the random variable of affected people at a random person. Okay, so in this case, we have an X for the patient 0, which is 3. Then we have an X for each one of them. And one of the things that we're going to assume is that these random variables are independent for each person. Okay, so what I'm saying is how many people does this guy infect is independent of how many people this person infects, and is independent of how many people this person infects. Okay, and then so on. Their offsprings will also have the probabilities, certain probabilities of infecting a quantity of people, and they are independent from each other. Okay, so what do I want to say here? So let's say that we have a couple of trivial examples. So let's say that the so pk, so let's say p of k is equal to the probability that x is equal to k. Okay, so this is the random variable of infected people. So we need to only give this probability function to understand how this branching process is going. So let's assume that p of 1 is equal to 1. So the idea is that each patient, each infected person, has probability 1 of infecting one other person. Okay, so then what we would get is that C0 is equal to 1. Then this person will infect with probability 1 one person. So C1 is equal to 1. Then this person will, with probability 1, infect another person, which will be 1. And then this person will have probability 1 of infecting one person, so C3 is equal to 1, and this keeps going. Okay, so this process never goes extinct. Okay, this is a really simplistic thing, but it kind of gives you an idea that this process is in the border between the process of getting extinct and not getting extinct. So if the expected value of x is less than 1, so the probability that you infect one person is less than 1/2. More than one person is less than 1/2. The probability that you infect more than one person is less than 1/2, is more likely you infect less than one person, then we will expect that the process goes extinct. Okay, so the previous case is how do you call it, on the boundary of survival. Okay, so there is survival here. I mean, of course, we do not want the virus to survive. The concept of survival has to do because instead of considering the virus, we could be considering, for instance, the last names of a person. So each parent has a certain amount of sons. These sons carry their last name, and then the sons will have kids of their own which carry their last name. So each C0, C1, C2, C3 have to do with the generations. Okay, so this is the original person, then this is the first generation, second generation, third generation, and so on. Okay, so we would expect that if the expected value of x, okay, so is less than 1, then the virus will go extinct. Okay, so here, I guess I'm not sure if you are how familiar you are with the models that have been in the news and these kind of things. Here, this E of x, the expectations of the number of people infected by a single person is what they call R0. Okay, so when R0 is bigger than 1, we expect this process to grow exponentially, and when R0 is less than 1, we expect this process to go extinct. Okay, so the social distancing rules that are being applied in certain countries is to reduce this number. Okay, so social distancing measures are trying to reduce the expected value of people infected by a single by a single patient. Okay, so this is how you control the virus. You control the virus by reducing the expected value of contagions from one particular person. Okay, so the particular thing of why in Brazil it seems to be growing exponentially is because there hasn't been taken any social distancing rules, which implies that then this process, instead of trying to go extinct, will actually try to cover the whole population. Okay, so let's look at a more formal definition. Let's say a Galton-Watson process or a branching process. A branching process is a family of random variables which is equal to z I from I equals to 0 up to infinity, such that Cn is equal to the sum from j equals to 1 up to the value Cn minus 1 of x, and let's call them here x n minus 1 j. Okay, so these are the infected people at level n minus 1. The number of infected people at level n minus 1, such that Cn is equal to this with x I j distributed like x, with distributed like x, where x is the original infection of the first person, and independent. Okay, so all of these variables xij are independent from each other. Okay, let's start trying to see what is the number of people. Okay, so Zn is equal to the number of people infected after 2 times n weeks. Okay, so we have to, we wanted to understand like an idea of what is the size of Cn. So then let's bring it back to what we had said before. And let's write the following lemma. suppose x has expectation of x equals to mu. Then then the expectation of Zn is going to be equal to mu to the n. Okay? So here, or let's call it R0, I guess, so that it ties up with what I was saying before. So this is R0, and this is R0 to the n. Okay, so E of Cn, the expected value, okay, so this is the expected quantity of people infected after 2n weeks. Okay, so what is the remark? If R0 is larger than 1, this quantity grows exponentially. Okay, so the larger the number of people you're likely to infect, then this guy, after a few generations, will become unmanageable. Okay, so for R0 large, for R0 much bigger than 1, so much bigger than 1 is something like 2 in this case, we would actually have a big problem after a couple of weeks, after a few months. Okay, so here I have given like this sort of doubling procedure to happen after 2 weeks, because that's just morally what is happening with the virus. But the thing is that this actually becomes a bit faster, because the people that get infected can keep getting infected people, and actually the people that got infected will start getting infected people right after they start. So okay, so instead of thinking of 2n weeks, maybe you should think of 2n days. Okay, and this is like the exponentially growing curve that you're actually seeing. Okay, so let's prove this lemma. And we'll do it by induction. Okay, so let's start with n equals to 1. N equals to 1 is equal to the expectation of Z1. But by our definition of what C1 is, C1, so this is the expectation of the sum from I equals to 1 up to Z0 of X0 I. Okay, but C0 by assumption C0 is equal to 1. So then this is equal to the expectation of X0I, but this is equal because we are assuming that Xij is distributed with value x. This is equal to the expectation of x, which is equal to R0. Okay, so this is the first step. So now we do it by induction, and we try to, so we consider Zn is equal to the sum from, let's say, I equals to 1 up to Cn minus 1 of Xn minus y minus 1 I, where Xn minus 1 I are identically distributed with distribution x. Okay? All right, so then what is E of Zn? So E of Zn is going to be, so now E of Zn will depend on the value of Zn minus 1. Okay, so then the expectation of Zn, and using linearity of expectation, we have that E of Zn is equal to the sum of k equal to 0 up to infinity of the probability that Zn minus 1 is equal to k times, so the point that what we are using here is that if we replace here Cn minus 1 by k, we can take the expectation specifically, and this is the expectation of the sum from I equals to 1 up to k of xn minus 1 I, like this, okay? But now we use that xn minus 1 I is distributed like x to say that this is equal to the sum from k equals to 0 up to infinity of the probability that Cn minus 1 is equal to k times k times the expectation of x, which is just equal to R0. Okay, so this is independent of the sum over k, but if we realize this thing here is just the expectation of Zn minus 1 times R0, which by inductive hypothesis, by inductive hypothesis, this is equal to R0 to the n minus 1 times R0, which is equal to R0 to the n. Okay. All right. All right, so then let's understand how important this R0 is. Okay. So I'll repeat, like, basically the idea of staying indoors is to try to minimize this R0, okay? And it's a probabilistic thing. It doesn't mean that you have the virus and that's why you're staying inside. If everybody stays inside, then you actually get this probability to go down, this R0 to go down. So let's look at the following corollary. If E of x equals to R0 is less than 1, then the probability of extinction is equal to 1. Okay, so how do we define extinction? So extinction, so I'll put the proof here, to start here. Extinction means that exists an n such that, so an n in the naturals, such that z n is equal to 0. So instead of calculating the probability of extinction, let's calculate 1 minus the probability of not extinction. Okay, so we are going to consider En, which is going to be the event that Cn is bigger or equal than 1. Okay, so these intersections overall n is the complement of extinction. Okay, so if we take the intersection from n equals to 1 up to infinity of En, this is the n equals to 1 up to En. This is equal to the complement of extinction. Okay, so this means that Cn is positive for every positive n. Okay, so this is exactly the complement of extinction. And so now what we can reduce ourselves is to understand what is the probability of En. Okay, the probability of En, so the probability that Zn is bigger or equal than 1, is less or equal than the expectation of Zn over 1. Okay, and this is Markov's inequality. Okay, so the probability that a random variable z, so this one has to be positive, is bigger than a, is equal to the expectation of z over a. Is it's not bigger or equal, is less or equal than this. This is Markov's inequality. Okay, but by the previous theorem or lemma, okay, this is equal to R0 to the n. Okay, this is by previous result. Okay, so now if we want to consider the probability of the complement of extinction, this is going to be equal to the probability of the intersection of En, this is n equals to 1 up to infinity, which in turn is less or equal than the probability of En for every n bigger or equal than 1. Okay, so the intersection of all of them is smaller than one of the particular events. So by knowing that this event is larger than this one, we know that the probability of the whole intersection is less or equal than this for every n, which implies this is less or equal than the minimum over n, bigger or equal than 1, of the probability of En, which is equal, which is less or equal than the minimum when n is bigger or equal than 1 of R0 to the n. But this is equal to 0 if R0 is less than 1. Okay, so what countries like China and Korea have been able to do is that they have been able to reduce, okay, so this is an observation, countries like China or South Korea have made have taken measures to make R0 less than 1, so they have forced extinction of the virus. So, okay, so these countries have forced extinction of the virus within their own borders, but now because the virus is in different countries, then the question is, do you have to actually keep these measures in place so that we actually keep this R0 less than 1 so that we have extinction? All right. Okay, so the probability of extinction is equal to 0, which is equal to 1 minus of the complement of extinction, which is equal to 1 minus the probability of extinction. Okay, so now we're going to go into something which is more on probability. So we want to understand this type of process. So the question now remains is, if R0 is less than 1, then we know what happens. The probability of extinction is equal to 1. Okay, now what happens if R0 is bigger or equal than 1? Okay, so one of the answers that we partially have given is that the expected value of this process is R0 to the n. Okay, so if R0 is bigger or equal than 1, this will grow exponentially. So the expected value is growing exponentially. But there is still a non-trivial probability it will go extinct. Okay, so what we're going to do through the next class is to understand, okay, so the point is, in a place like Brazil, we clearly are having an R0 bigger or equal than 1, but we could actually be lucky and actually see that the virus disappears all of a sudden just because of these probabilities, just because there is a chance that this virus will go extinct if this R0 is controlled within some reason. Okay, so for this, to calculate this probability, explicitly, we will need the generating function. Okay, so let's start with the definition. The definition is that the generating function function g from R to R of a random variable. So let's call it gx of a random variable x is defined by gx of s is equal to the expected value of the function s to the x. Okay, this looks a little weird, but the idea is that taking taking expectations of nonlinear functions applied to your random variable characterizes its distribution and might be easier to handle. Okay, and this is something that we're going to see. So this type of generating random function is good. Okay, so the generating random function is good to handle sums of identically distributed random variables. Okay, and then this is exactly the point, is that Zn is equal to the sum of Cn minus 1 of this xi. So the idea is that the generating function of Cn will have to do something with the generating function of Cn minus 1 and the generating function of xi. Okay, so this is something we're going to do in a little bit. So this is just to motivate why we want to look at these type of things. But let's first look at an example. Examples, so let's say that x is a Bernoulli variable with parameter p. Okay, so this is f, so p, the probability that x is equal to 1 is equal to p, and the probability that x is equal to 0 is equal to 1 minus p. Okay, so if we take gx of s, this is going to be the expectation of z to the x, which what we have seen from previous classes, this is the sum of k equals to 0 up to infinity of s to the k, the probability that x is equal to k, which in this case for this specific variable is going to be s times p plus when s is equal to when k is equal to 0, this is equal to 1, so this is going to be 1 minus p. Okay. Now, for another example, let's consider the example of a Poisson distributed random variable with parameter lambda. So gx evaluated in S is going to be the expectation of Sx, which is going to be the sum from k equals to 0 up to infinity of s to the k times the probability that x is equal to k, which in this case is lambda to the k e to the minus lambda over k factorial. So now we can realize that this term here is independent of the sum. So here we get e to the minus lambda, the sum of k equals to 0 up to infinity, and now s and lambda are raised to the same value. So this is s lambda to the k over k factorial. So what we realize is that this sum is equal to the exponential of s lambda. Okay, so what we end up getting is that this is the exponential of s minus 1 to the lambda. Okay, so this is something I'm not quite going to show here, but this the generating function completely characterizes the distribution. So if we have some random variable that has this as their generating function, then it implies that they have this distribution. Okay, so sometimes knowing what the generating function looks like implies what is the distribution of the particular x. So if we have a generating function that looks like this, then we actually know that your original random variable was Bernoulli with parameter p. So this is a roundabout way to sometimes guess what is the distribution of a central random variable, if it's given by sums or if it's given by different things, in which we can actually guess what the generating function is. Okay, so let's look at the theorem. Generative random function is good to handle sums of identically distributed random variables and independent, identically distributed independent. Okay, and so let's look at the independent part of this thing. So theorem, if x and y are independent, if x and y are independent, then the generating function of x plus y evaluated at s is going to be the generating function of x at s times the generating function of y at s. And let's look at the proof of this. Okay, so this is what is nice. So because we have this exponential, the exponential of the sums become product. Okay, so this is just a reminder. Exponential of sums become products. Okay, but here we have the independence. Okay. So what is the proof of this? So g of x plus y evaluated at s is going to be the expectation that of s x plus y. But okay, exponential, the exponential of x plus y is going to be the expectation of sx times sy. Okay, now the next thing that we need to realize is that if x and y are independent, then any function applied to them, so we are saying f of x and g of y are also independent. Okay, Therefore, Sx and Sy are independent. Which implies that the expectation of Sx times Sy is equal to the expectation of Sx times the expectation of Sy. Okay, this is by theorem in previous class. Okay, if we have independence of the random variables, we can take the product, but this thing here is just g of x at s times g of y at s. Okay, now let's consider something a bit more general. Okay, so this is more of a theorem related to the branching process that we were looking before. If t is equal to x1 plus x2 plus xn, where n is a random variable independent of x I equals to 1 up to infinity, let's say. So n is a random variable independent of xi I equals to 1 up to infinity, which are independent and identically distributed with distribution xi like x, then the generating function of the random variable t, g of t at s, is going to be the generating function of n applied to the generating function of x evaluated at s. Okay, so this composition here. So the proof is similar to what we have done here, and specifically for the expected value of Zn. So what is the proof of this? The proof is gt of s is the expected value of s to the x1 plus x2 plus xn. Okay, but now the expected value of this guy is depending on n. So again, using the linearity, this is going to be the sum of n equals to 0 up to infinity of the probability. So here we are using the fact that these guys are independent to say that this is the probability that n is equal to little n of the expectation of s to the x1 plus all the way up to x little n now. But by the induction, by the theorem here, we can do an induction to say that if we take independent, identically distributed random variables, so here maybe I can write a corollary. So if xi are distributed like x iid, then this g of the sum of xi I equals to 1 up to n of s is going to be g of x of s to the n. So here, what we get is that this is the sum from n equals to 0 up to infinity of the probability that capital N is equal to little n of g x at s evaluated, and all of this to the n. But now if we realize what's going on here, so this thing here is coming here. So what we are realizing this is the expectation of n equals to 1. So if we think of this now is a fixed number. Which we are exponentiating to the n. So this thing here is the generating function of capital N. So what we get is that gt of s ends up being gn evaluated in gx of s. Okay, so now let's look at the corollary. If Zn is a Galton Galton-Watson process, then it's a Galton-Watson process. What we are going to get is that g of z n is equal to g, let's call it little n here, of s, where this is a shorthand notation for saying g of x composed with g of x, composed with g of x, composed with g of x, evaluated at s, and this composition is n times. Okay? So this is now the Gn of s. So proof. And again, we are going to show this by induction. So by induction, so first for n equals to 1, g of z1 is the same as, so c1 is just equal, the distribution of c1 is the same as the distribution of x, so this is g of x at s. Now, if we look at Zn is equal to the sum from I equals to 1, Cn up to Zn minus 1 of xn minus 1 I. So then g of Zn at s by the previous theorem, is equal to g of Zn minus 1 applied. So this is now my capital N. And now we have to put the distribution of these guys, which is Gx of S. Okay? But this thing here is by inductive hypothesis. G of Zn minus 1 is equal to Gn minus 1, which again, this is just the composition of G of x n minus 1 times. Okay, so then if we have Gn minus 1 composed with Gx of S, this is just going to be Gn of S. Okay, so why do we care about this guy? So first of all, there's another observation that we should make. The observation is that Gx of 0 is actually equal to the probability that x is equal to 0. Okay, so why is this? So what is Gx of S? Gx of S is the expectation. Okay, so it's going to be the sum from k equals to 0 up to infinity of S to the k, the probability that x is equal to k. But now, if we take S equals to 0, so if we take k equals to 0, so the point is that, so if we take the limit when S goes to 0 of S to the 0, this is equal to 1. Okay, because this is equal to 1 for every S positive. So in particular, the limit when S goes to 0 of Gx of S is just going to be equal. So all of the other numbers when S equals to 0 where k is positive, so the limit when S goes to 0 of S to the 0 is equal to 1, and the limit when S goes to 0 of S to the k is equal to 0 for every k bigger or equal than 1. So in particular, the limit when S goes to 0 of Gx of S is just going to be equal to the probability of x is equal to 0. Okay, therefore, the probability that Zn is equal to 0, so this is the virus got extinct after n steps, is equal to G of Zn at 0, which is also equal to Gn at 0, which is just G of x composed with G of x composed with G of x at 0. okay, which is just the probability of x is equal to 0. Okay, so the idea is that if we actually know something about the distribution, only about the distribution g of x, we can calculate explicitly what is the probability that we actually going to get extinct after n steps, or we go to get extinct in general. Okay, so yes, I'll go a bit more. And let's look at the properties of G. So we're going to look at the properties of G of x in general, and let's look at the following things. So one of them is going to be that G of s is increasing in R plus. The second one is that G is convex in 0, 1. And the third one is that G prime, okay, so let's call it G of x, G prime of 1 is equal to the expected value of x, which is equal to R naught. Okay, so what is the proof of this? So the proof, let's go for I. If s is less or equal than t, so it's like is increasing here, it would be is non-decreasing. If s is less or equal than t, then s to the x is less or equal than t to the x, because x is positive. Then the expectation, so the generating function of x at s, which is equal to the expectation of s to the x, is less or equal than the expectation of t to the x, which is equal to gx of t. So if s is less or equal than t, then the generating function at s is less or equal than the generating function at t. Okay, now let's look at the convexity. So convexity means that G of x at let's call it lambda times s plus 1 minus lambda 1 minus lambda at t has to be less or equal than lambda g of x at s plus 1 minus lambda of g of x at t. Okay, and this is lambda, a parameter between 0 and 1. Okay, so if we make a drawing, this is R plus or 0, 1, let's say, and this is gx. So g of x has a shape like this. So the idea is if we take a value here s, we take a value here t, and we take the line here, the value of g at the point in the line, this is lambda s, so sorry, here, this is lambda s plus 1 minus lambda times t, we have that g at that value has to be less or equal than the line intersecting the secant line between g of s and g of t. Okay, so so how do we prove this? So the idea is to take gx at lambda s plus 1 minus lambda t, which is just the expected value of lambda s plus 1 minus lambda t. To the x. Now, this is equal to the sum of k bigger or equal than 0 of p, the probability that x is equal to k, of lambda to the s plus 1 minus lambda to the t to the k. But now the idea is that the function let's say f k of s equals s to the k with k bigger or equal than 1 is convex. Okay, the way that you can check this is by taking the derivative. So the second derivative of fk at s is equal to k times k minus 1 times s to the k minus 2, which is positive if k is bigger or equal than 1 and s is bigger or equal than 0. Okay, the case k equals to 0, this is just equal to 1 and it's constant. So in particular, it's convex for k equals bigger or equal than 1 and k equals to 0. Okay, so there is a change of convexity at the point k equals to 1 and k equals to 0. Okay, so for k between 1 and 0, you actually don't have convexity. But in this case, because we are away from the set, we actually have convexity of this function. So in particular, we have that lambda s plus 1 minus lambda t to the k is less or equal than lambda s to the k plus 1 minus lambda times t to the k. This is by convexity of fk. Okay, so in particular, what we have is that gx of lambda s plus 1 minus lambda t is going to be less or equal than the sum of k equals to 0, and here I'm going to put the lambda outside, lambda times the probability that x equals to k, s to the k, plus 1 minus lambda, the sum of k equals to 0 up to infinity of t to the k times the probability that x is equal to k. And this is just the generating function of lambda times the generating function at s plus 1 minus lambda, the generating function at t. Okay, and that's part 3. Part 2. So for part 3, we're going to wave our hands a bit. But, okay, so let's see what g of x at s is equal to the sum of k equals to 0 up to infinity of the probability that x is equal to k times s to the k. Now, if the series is absolutely convergent, we can differentiate term by term. So what do I mean? So if I take the derivative of g x with respect to s, then I can take the derivative of each of these terms. Okay? So assuming this, we get that gx prime at s is going to be the sum from k equals to 0 up to infinity of k times the probability that x is equal to k times s to the k minus 1. In particular, if we take gx prime at 1, this is the sum from k equals to 0 up to infinity of k times the probability that x is equal to k. And this thing here is equal to 1 because we are evaluating an s equals to 1. But this you can translate exactly as being the expectation of x, which in this case is just equal to R0. Okay. Now, what do we need? So let's look at the following theorem, and then I think we'll finish the class here. This is a bit long of a proof, I guess. So let's look at the following theorem. Following theorem says if Zn is a Galton-Watson process, then eta equal to the probability of extinction is the least the smallest no negative solution to gx of eta is equal to eta. Okay, so the point is, what is the probability of extinction? So here, I guess there is an extra property which I'll leave as an exercise for you guys. If I can find the page I'm looking for. Anyways, so as an exercise, check that gx of 1 is equal to 0. Gx of 1 is equal to 1 for every random variable x. Okay, so if here we have 1, here we have 1, here we have 0, and here we have the probability that x is equal to 0, which is a positive thing. So what we are going to have here is that g of x is a convex function that is going from here. It's an increasing convex function that is going from here to here, and eta is going to be the smallest solution of g of eta equals to eta. Okay, so there is always going to be a solution here, which is gx of 1 is equal to 1. And now the question is, if we have extinction, the probability of having extinction is less than 1 if there is another solution to this equation. Okay, so we always have, there is always one solution. But we could actually have another solution, and the question is, if we have another solution, can we actually check? So if we have another solution, can we actually check that is actually strictly less than 1? Okay, so let's do the proof of this. Okay, so what we have is that eta, so we are going to construct an increasing sequence eta n that converges up to eta, and we are going to show that eta has to satisfy the right equation. Okay, so what is eta n? Eta n is the probability that Cn is equal to 0. Okay, so that the virus went extinct after n steps. So that the virus already went extinct after n step. Okay, so what we have is that Zn minus 1 is eta n minus 1 is less or equal than eta n, because if Zn minus 1 is equal to 0, this implies that Cn is equal to 0. Okay, and so this implies that we have an increasing sequence. Okay, but what we saw before, the probability that Zn is equal to 0 is equal to the generating function of Zn at 0, which is the same as Gn of 0. So what we get is that eta 1 is going to be Gx of 0. Eta 2 is going to be Gx of 0, but this is just Gx of eta 1. So if we follow this sequence, what we're going to get is that eta 3 is just going to be gx of gx of gx of 0, which is just equal to gx of eta 2. So on, we get that eta n plus 1 is just gx of eta n. And this is an increasing sequence. So let's take, what we know is that g of 0, so eta 1, is equal to gx of 0, which is less or equal. Okay, so before we keep going here, we are going to call eta star the probability of extinction, and the solution is gx of eta star is equal to eta star. So eta 1, and okay, so one of the things that we know is that eta star is bigger or equal than 0. So what do we get here? Eta of 1, g is equal to g of x of 0, which is less or equal than gx of eta star, which is equal to eta star. And here is because 0 is less or equal than eta star, and g of x is increasing. Okay, but now we can keep going with the same argument, and we realize that eta 2, so from here we can say that eta 1 is less or equal than eta star, so eta 1 is less or equal than eta star. Now g of eta 2 is equal to gx of eta 1, which is less or equal than gx of eta star, which is equal to eta star. So this implies that eta 2 is less or equal than eta star, and so now we realize that eta 3, which is equal to gx of eta 3, is less or equal than gx of eta star, which is equal to eta star. So in particular, eta 3 is less or equal than eta star. So in particular, eta n is less or equal than eta star for every n. So now, and this is something I guess I can ask you to prove yourself, or you can just actually check it by the convexity, is that now what we have is that because gx is convex, this implies that g of x is continuous, and if not, check that g of x is continuous. Okay, so then eta, which is going to be the limit on eta n, so this exists because eta is increasing. So it exists because eta is increasing, and This is the limit when n goes to infinity of g of eta n is the same as the limit when n goes to infinity of gx at eta n minus 1. But again, using the continuity of g of x, we can pass this inside by continuity, which implies that g of eta, this is equal to g of eta. So then eta is a solution to the fixed point equation. Eta equals to g of eta, and eta is less or equal than eta star, which is, so this is also positive, which is the smallest non-negative solution. So if we have a solution which is smaller than the smallest non-negative, if we have a non-negative solution which is smaller than the smallest non-negative solution, this implies that eta is equal to eta star. Okay, I guess to finish the class, let's look at the corollary. The Galton-Watson process has probability of extinction less than 1 if and only if R0 is bigger than 1 or x is identically equals to 1 almost surely. Okay, so it's the process that we had seen earlier in class in which each person actually infects exactly one person at every step. Okay, so this is what I was saying, this is a process that separates one from the other. Okay, so what are we saying? So what we checked from the theorem is that the probability of extinction is the smallest non-negative solution to this problem. So one of the things is that we are going to assume that the probability that nobody gets infected is actually positive. Okay, so what do we have? We have so the proof. We have G, which is going G of x, which is going from 0, 1 to 0, 1, which is continuous and continuous, convex, and increasing, such that G of 0 is positive. So the point that G of 0 is positive, this is the same as assuming, this is assuming that the probability that x is equal to 0 is positive. So this would be if the probability that x is equal to 0 is equal to 0, then extinction is impossible. Okay, if the probabilities, we actually get that the extinction can be impossible because all of the persons that are infected will actually keep infecting more and more people. So g of 0 is positive, and g of 1, gx of 1, is equal to 1. Moreover, if the expectation of x is equal to R0, which is positive, then g prime x at 1 is going to be the expectation of x, which is equal to R0, which is, this is bigger than 1. Which is bigger than 1. So the derivative at this point is positive. So if we do the graph that we were looking at before, so here we have s, here we have 1, here we have 0, here we have 1. So if here we draw the line the straight line, then what we have is for g prime so this is the picture, around here is the picture of g x of 1 is equal to 1, and this slope here has to be bigger than the slope coming from the identity here, and this slope here is gx prime of 1 is actually bigger than 1. But now if we assume that g of x of 0 is here, which is the probability that x is equal to 0, then we have a continuous convex function which is increasing, so then it has to look like something like this, and this point here is eta star, which is strictly smaller than 1. So the idea is, as I told you, there is always one trivial solution, which is g of 1 is equal to 1. But then the point is, can we find that there exists another solution in the middle? So for a continuous convex and increasing function, if we know that the right derivative is bigger than 1, then we can actually show that there exists another solution. Eta star is now between 0 and 1. Okay, and so basically, if we want to prove this, using gx of 1 is equal to 1 and gx prime of 1 is larger than 1, it implies that there exists an epsilon positive such that g x of 1 minus epsilon has to be less than 1 minus epsilon. Otherwise gx prime of 1 is less or equal than 1. Okay, so what is this? This is the limit when epsilon goes to 0 of gx of 1 minus gx of 1 minus epsilon over epsilon, and this is what we are assuming that is bigger than 1. And now if we actually check that this is equal to 1, we can actually check that this limit being bigger than 1 implies that there exists an epsilon, let's call it epsilon naught, such that this guy is less than this. So what I'm saying is consider here 1 minus epsilon naught. Here you are below the curve. Here at 0 you're above the curve. At 0, gx of 0 is bigger than 0, then there exists by the intermediate value theorem, there exists eta star in between the 0, 1, such that gx of eta star is equal to eta star. Okay, so let's look a bit. So this proves one part of the theorem. So let's look at this. So if zeta n is a Galton-1,2 process, so eta star, sorry, this is not the theorem I wanted. So the corollary that we're trying to prove is the Galton-1,2 process has probability of extinction less than 1 if and only if R0 is bigger than 1 or x is exactly 1. Okay, so one of the things is if R0 is less or equal than 1, then we know that the probability of extinction is 1. Now, if R0 is bigger than 1, we have just shown that the probability of extinction is equal to 1. So now what we are missing to show is that if R0 is equal to 1 and the probability of extinction, so we are missing to show that if R0 is equal to 1, this is the expectation of x, and the probability of extinction is less than 1, this implies that x is identically 1. So, how are we going to do this? We are going to do this by using Jensen's inequality. Jensen's inequality says that the expectation of s to the x is bigger or equal than the s to the expectation of x. But in this case, this is just equal to s to the r0, where r0 we are assuming to be 1. So this is just equal to s. And this here is the generating function of x at s. Okay? And so this inequality is Jensen's inequality because s to the little x is a convex function. Okay, so this is Jensen's inequality. And in particular, we have equality if and only if So because this is strictly convex, we have equality in Jensen's inequality if and only if x is identically equal to the expectation of x, which is equal to 1. Okay, and this actually shows you what we are trying to show. So if we have the probability of extinction, if the expectation is equal to exactly 1, then the probability of extinction is going to be 0. The probability of extinction is going to be 0 if and only if x is identically equals to 1. Okay, and I think that will be done for this class, and then I'll try to upload one a bit later.